So this year at my talk, I'm gonna kind of go over my vision for Wasm as a debugging target. I talked a bit about this last year at Wasm Research Day about our instrumentation and some database detection framework that we had. Um, but this year I'd like to go into more details because we have more results and we have like a much more interesting perspective on how Wasm can help um, debugging across different domains. So to start off, as we know, debugging is real hard and it's often highly domain specific as well. When we take a look at applications that we design, we often have to deal with, complex task synchronization, locking, message passing, fork joins, and often even with language interoperability. Um, Today people are designing applications with a combination of a lot of embedded style um, targets like Rust, C, and even Zig. When we look at the hardware, there's additional complexity that comes in. We often have unreliable networks. We can have networks that drop. We can lose connection. We need to have fault tolerance to these things. And we also deal with heterogeneous and resource-constrained devices. A lot of times, being able to bootstrap something on a microcontroller and edge system is much harder than that of, more powerful devices. And finally, when we take into account domain specificity, all of this gets even harder. Because when you have to look at, tailoring a debugging platform for a real-time system, you need to deal with the overheads and make sure you don't have high jitter. For distributed cyber-physical systems, you often need to deal with unpredictable physical environments, which is often hard to model in simulation. And finally, even if we take a look at running applications on our local machines, if you want to deploy things into the kernel, it's often hard to get observability into applications running in the kernel. So given this setup for debugging, why do we want to use Wasm as a debugging target? I would like to say it's because, GPT believes in us. Um, but the reality is that there are a lot of nice properties that make Wasm usable for debugging. In particular, the simple representation and instrumentation capability for Wasm, and its platform portability and agnosticity to compilers, languages, and CPUs, make it a nice and easy portable target that you can use to compile all of your source level languages to this intermediate target, do all of your analysis, and then execute it across all your different platforms. In particular, I think one hindering factor in a lot of use cases for Wasm has been the bring up of Wasm. So while it does have high domain flexibility in terms of, you could implement any system API you want over Wasm, it's often quite hard to bring these up in practice, as I'll show in some of the later slides for some of the distributed cyber-physical systems work we've been doing at Bosch. And just to kind of give you a teaser, this is a heterogeneous test cluster we have set up at CMU in our lab. We have around 20 plus devices that range across RISC-V, ARM64, and x86 targets. As you can see, we have a lot of different CPUs as well. We have some redundancy in terms of, a couple of 4 Tiger Lake devices on them as well. And this has been really useful, and we've actually been able to get Wasm set up and running on all of these devices, which is really cool. So I think really the key idea I've come to over the years of using Wasm is Wasm provides this really nice narrow waist between these high-level programming languages and the platforms you want to target. In particular, Wasm itself as a language has been evolving really well, but there's often pieces in the pipeline here that are missing, particularly with development of compiling source code applications to Wasm, and also with deployment, with how do you deploy Wasm effectively and what can you do at deployment with Wasm. In particular, there are a few ideas we've explored here. With the development side, there are things you can do with interfaces for Wasm and the programming model and so forth. In particular, in this talk, I'll focus on one, which is the WebAssembly Linux interface, which I've designed along with Ben at CMU, and talk a bit forward-looking about how we could potentially have interfaces for CPS-style domains and even the kernel, so we can run Wasm safely in the kernel. And on the deployment side, I'm going to talk a bit more about, debugging, profiling, fault tolerance, and all of the stuff you can do, focusing a lot more on data race detection, which I talked briefly about last year. But now we have more results and we can show you some hopefully cool stuff. And forward looking again, a bit on record replay. I know you guys had the Wasm R3 talk right before this. So that was a nice, I think, intro into all of this. And yeah, and we can talk a little bit about, where that would go moving forward. So to start, I'll focus on the first half of the pipeline, particularly the WebAssembly Linux interface. So our goal here was a debugging target is only as effective as things that can compile to it. And so at the end of the day, if we have applications and we're not able to effectively compile them to our target, it doesn't serve as a good platform for debugging. So on that note, I have been extensively using Wally in my work, just as a way to easily bring up a lot of applications from different source languages to Wasm, particularly with a lot of feature completeness. So WASI is great, and I think WASI provides a really good capability-based model that is useful when you're trying to run things in a secure environment. But I think as a lowest system interface, it has limited capability enough. It makes it hard for you to target it nicely as a debugging platform. And to also add on, the implementations of WASI are becoming increasingly complex, especially as we're moving to Preview 2 now. And they can be quite non-trivial and buggy. There's actually, I think, one paper, the WAVE paper, that talks about verifying WASI interfaces through formal verification, and they found, a bunch of sandbox leakages through like proc mem accesses and so forth. So our insight here is that Wasm really should be treated kind of like a virtual CPU, where we support low-level syscall or stable platform interfaces, and we can build up the higher level capability-based interfaces over the system interface. So what this layering actually enables is for us to run WASI in Wasm, which makes it robust to, remote code injection attacks. It gives it control flow integrity. It also gives it the portability across all of the architectures and engines we support, which I think would be a huge boost to WASI and its adoption across the ecosystem. So kind of just highlighting that the Wally layer itself allows you to compile any Linux application to WebAssembly. If you're only targeting WASI, it would use the restricted subset of WASI, essentially having that layer virtualized over Wally as a Wasm module. And this really makes Wasm a nice target for a number of different languages. I think so far we've gotten Virgil, Lua, and a couple more languages, and Bash, like shells, to compile over Wasm, which has been, I think, really cool. And just to kind of give people an idea of the portability effort to actually get applications to port over Wally, it's essentially almost minimal. There's usually no source code modifications we have to make to actually get things to compile. And kind of a really nice thing is while we were doing this, we looked into actually supporting the Linux test project, trying to get all of the syscall tests within the Linux test project to actually bootstrap over Wally and see how much of that we could pass. And if we actually looked into this Linux test project, it's a seriously complicated test harness, which uses a number of things like signals, users, groups, forking, communicating over shared memory. And essentially, we can transparently support all of this over WebAssembly now, which is kind of alludes to the feature completeness of Wally and how it can really benefit in targetability to Wasm. So looking forward, Wally really has been for user space Linux applications. Obviously, not everybody is doing only Linux and only user space. So one of the things we've been looking at is dropping Wasm into the kernel, particularly kind of like an eBPF replacement. So you can do ultra low latency RPC within the kernel, or maybe do some fast packet processing. And Wasm is formally verified and it's machine checked. And I mean, it's machine checked and it's a sandbox and it has all of these really nice properties that make it a nicer replacement, in my opinion, to eBPF. And in cyber physical systems, so I am collaborating with Bosch, as mentioned earlier. We have done some work on creating interfaces to automation data layers that are actually used to communicate with field bus I/O devices, commonly used in industrial automation. And this can help Wasm penetrate the cyber physical ecosystem, essentially, running embedded applications in the world. We're also looking a bit into supporting real-time operating systems because that seems to be embedded seems to really be a useful domain for Wasm at the time. And kind of two other things I've been recently looking into is ROS and PLC. These are very common domains that are used in robotics and automation again. So it could really be useful to create direct interfaces from Wasm to these to do analysis, profiling, sandboxing, or any of that nice stuff we want for applications deployed in the wild. So kind of just to give you an idea of Wasm in industrial automation, because I think we showed this video 2 years ago, but I'm sure there's a fresh crowd now. We're basically running this really ginormous, dangerous pendulum using Wasm, powering it through Wasm and the Control-X data layer, essentially. Cool. So now that we've kind of focused on like the start of the pipeline, now that we can actually target Wasm, I want to talk a bit about what we can do with a Wasm binary at deployment, focusing particularly, like I said, on data race detection. So just to give, so that everyone is on the same page, to give people a background on data race detection, what I mean here is essentially two threads communicating, over locks or some sort of shared memory. And you have a data race when you have some sort of shared resource, in this case, memory, where you have concurrent accesses with at least one write that isn't appropriately synchronized. So if we kind of look at the three examples on the right, the first one is clearly a data race because we have no sort of synchronization between those interleaved accesses to the memory access X. The other two are actually safe code because we have a mutex to lock exclusive access to X on the second case and a fork join implicit ordering on the third one. But to detect data races is quite hard. And in fact, more than detecting it, it's really hard to reproduce it. So once you actually do see them, you often find it hard to reproduce it when you want to, poke in and debug it, which is often why they're called Heisenbugs. So my focus on data race detection has been on one specific type of data race detection called delay injection. And the way this thing works is actually not to do anything statically or, determine ordering dynamically, but rather to let applications run and detect data races when they occur by having a short probing window during which you look for, concurrent accesses. The idea being if you have some sort of ordering or exclusive accesses, you can't have a concurrent access to a specific memory address during that short delay period when you probe. And so you can be guaranteed that you don't have false positives here, and everything that is a violation is potentially a data race, although it may be benign. So there are actually a number of techniques that have utilized this sort of delay injection approach. The most recent is kind of TSVD, which was deployed at Microsoft. And they do this thing with C# where they do essentially this algorithm and they detect a ton of bugs across Microsoft code bases, which was extremely useful for them. But in particular, when honing in on these techniques, I noticed a couple of things. One is these techniques are often inflexible because they're language specific. So the Microsoft thing, for example, was C#. Some of them require hardware extensions. So Data Collider actually requires you to have special registers that are reserved for this delay injection technique. And I think the second thing that's kind of hard to quantify in these is that it's hard to tune. So if you're someone, say, deploying a real-time application and you can only, you have a hard deadline that allows just maybe 20% slack. You want a system where you can say, use all of my 20% slack towards, debugging. And I don't really want something that's unpredictable and has high jitter. And so I think in a lot of deployment use cases, the tunability is kind of a critical factor in adopting this at deployment, or even at production, I would say, if you're trying to work within a specified compute budget. And finally, I think the most important thing is how do you quantify the effectiveness of these debuggers? Because oftentimes when you look at people evaluating a debugger, they report the number of bugs they found, which is maybe they found 50 bugs, but you don't actually know the ground truth. You don't know if the code had 1,000 bugs and you only found 60. In that case, is your debugger really effective? So kind of what we want to look at is, can we quantify the effectiveness of a debugger? And in particular, I would say the effectiveness of a debugger comes down by its ability to detect Heisenberg bugs, because common bugs are things that are easily reproducible and easy to detect and are usually fixed before deployment. It's usually the Heisenberg bugs that remain, and you don't really have a solid ground truth to say whether these bugs actually exist in the code or not. So kind of with this motivation, we've looked into harnessing Wasm for data race detection, particularly to address those 3 points I mentioned earlier. The language agnosticity allows you to easily use it across a variety of source languages and also use it across domains. So, you could use this for applications over Wally, you could use it over things for the kernel, cyber physical systems, and so forth. And kind of our core insight is to actually enable platform and instrumentation diversity fuzzing to observe Heisenberg bugs. So what we mean by this is, since Heisenberg bugs only occur on very specific deployments, we want to explore the state space of deployments by running with a variety of instrumentation schemes and a variety of platforms. And the idea being we choose some random subset of platforms and some random subset of accesses to instrument and, see what types of bugs we can detect. And often, I think the first intuition for people is if we choose, a smaller subset than 100%, we have less effectiveness in our debugger. And while this is true, we can actually compensate for this with scalability. So instead of debugging with 100% of accesses instrumented on a single platform, you could instrument, say, 10% or 20% on 20 different platforms. And the scalability will compensate for your lack of instrumentation. And so with these ideas in mind, we essentially designed kind of like this prototype framework where we have the ability to mask certain accesses that we want to instrument and choose which platforms, we want to deploy across. And essentially in this case, we run this entire system over our cluster I showed earlier with 20 plus devices. So we have some really interesting insights coming up here, but it does require a little bit of theory, I want to call it. So I try to, water it down a bit and make it very easy to understand, but hopefully this is something that makes sense and is kind of interesting. So by running our data race detection framework across our entire cluster, we tried to come up with this notion of what we call a Heisen factor. And this Heisen factor essentially is a metric that quantifies the degree to which the execution environment of a program affects the observability of a given bug. And in our opinion, the Heisen factor is a great way to model a bug because you often have cases where, say, you have a million cars deployed and you have one specific car where you have bugs that are hard to reproduce. And in particular, bugs like that are bugs that you would intuitively call ones with a high Heisen factor because the observability of that bug is highly dependent on the platform or the specific circumstance under which the program is running. To qualify the words that I'm using in more detail, there are two specific things I want to highlight as well. One is the detectability of a bug, which is kind of what most people think of when they think of bug finding, which is, what is the probability of me detecting a bug if I run my debugger on this piece of code? The observability, though, is the probability that we detect a bug given that it's instrumented. That is, given that we are able to look at this snapshot of memory accesses. How easy is it for us to observe this bug? So essentially, observability in our case is akin to reproducibility. A highly observable bug is usually highly reproducible. And so kind of with this basic theory, hopefully the rest of this talk will make sense. We collected a data set with about 2 million runs across our entire cluster. So we have kind of a strong statistical backing coming up. So one of the core insights that we found was really, really interesting is that the observability of the bug is far from uniform. So often when people build debuggers, they work under the presumption that observability is uniform. That is, if I instrument my code more, I am likely to find bugs better. But what we actually see with our case is most bugs aren't uniformly observable. So if we look at, the ones in red, it's about when we run across different devices, we actually see very few bugs are uniformly observable. And when we vary the instrumentation, we see more, but it's still, less than 1/3 of the bugs are actually uniformly observable. So what we have on the x-axis is essentially bugs. Each column is a bug, and running along each column is the devices on the top graph and the density on the second. And actually, a lot of bugs are highly non-uniform in observability. So if we look at the ones on the real far right, we see that there are very strong peaks at specific platforms or specific instrumentation densities, which means that you will only ever see this bug if you ran under an execution environment that was similar to those modeled in those specific deployments. And a result of observability being so highly non-uniform is the fact that your detectability can be much higher on a specific platform, even if you don't have maximal instrumentation. So if we look at the two examples we see on the left here, an ordinary bug is what most people would expect when they're modeling debuggers. That is, as you do more intrusive debugging, your detectability, your ability of the debugger to detect that bug increases. But this isn't the case for a Heisen bug, where you actually have a very strong peak at a few specific deployments. And actually, if you did the most intrusive debugging in the case we see here, you would never observe the bug, which we think is counterintuitive and kind of very interesting. And zooming in on like one specific benchmark we used, we can see this kind of in more detail with some numbers, where we have the uniformly observable bugs on the left and the non-uniform observability on the right. And we can see strong peaks at, say, 30% instrumentation density for the final bug on the right. And so this is actually a really powerful insight that most debuggers don't use today, because it kills two birds with one stone. One is you're able to detect Heisen bugs effectively, and you're actually able to detect it with a lower overhead than you would if you were to run it, with a maximally instrumented module. So this actually gives you a lot of advantages in your debugger to be both more effective and lower overhead. And kind of just to not overwhelm people, but we have like a profile of all the bugs we found, and a lot of these graphs are really super interesting to look at. I'm obviously not going to go into everything in huge detail, but I'd like to highlight a couple of interesting detectability profiles we came across. So one is something like this, where you have detectability only across one row of your bug. And what that means is you're highly detectable on a single device, but nowhere else. So for example, if that was a RISC-V platform, this bug would only occur on the RISC-V platform, and you would actually never see it if you were to run it on any other platform. Then you have things like the one in the middle, where there's really no pattern here. There is high detectability. Like the one on the left, you can actually see can be detected at a lot of various different things, at a lot of various different points. But there's no clear pattern in terms of how the observability relates to this. Again, if you fuzz with instrumentation and platform, you have a higher likelihood of hitting one of these high detectability areas and actually finding these bugs. And finally, with the last profile, we see that we actually see the strong four device band at the bottom. And that corresponds to the profile of four Intel Tiger Lake devices that we have that are mostly, I would call, homogeneous. I think one is an i5 CPU, the rest are i7. But this kind of shows how much platform diversity actually impacts the detectability of your bug. So if you build a debug farm that has only a single homogeneous platform, you're probably missing out on a entirely large state space of Heisenbergs bugs that would never be found on your debug farm. And finally, what we actually see is that a lot of the rare bugs, that is the bugs that have low detectability, do end up being Heisenbergs bugs. You often don't have common bugs that are sorry, I meant to say you often don't have Heisenbergs bugs that are too common. So kind of we see these three, on the graph on the left, we see these three areas on our probability of detection. And the one is essentially, easy and common bugs that you will always see with the detection probability of 1. And the ones in the middle are kind of ones that are uncommon, but are mostly ordinary because they behave similarly as you change either instrumentation or device. But then the really rare Heisenbergs are ones that are only found when you change both your devices and your instrumentation. And kind of the graph from the left shows you that when you have that low conditional observability, you actually get a lot of bugs that have a higher Heisen factor and are actually higher to estimate as well, which means the benefit of using both platform and instrumentation diversity is critical for a debugger to be effective. And to summarize, basically with all of our insights, we ran a couple of simulation debug campaigns, and this is a summary of a debug campaign across specific compute budgets. And what we see is essentially, that device diversity and instrumentation diversity together produce a much stronger debugger than using either any one of them without the other, or using just homogeneous devices without any instrumentation diversity. And our takeaway from this is that when you build a debugger for debug farms, you should actually use a combination of weak and powerful devices. And it's kind of counterintuitive because, 10 server scale devices actually make your debugger weaker than, say, 4 server scale devices and 3 single board computers and 3 microcontrollers, because you get that much diversity from your platform and instrumentation. And finally, we actually even ran this with a handicapping, where we took the baseline being we instrument all of our accesses, and we try to cap the amount of accesses we can instrument. This comes back to the point I had made about tunability of our debugger. Oftentimes you might want to tune our debugger to say, okay, just allow it to instrument at most 20% of your accesses. And we see that even with handicapping, oftentimes you can produce results that are almost as good or even better than a debugger that uses instrumentation on all of the memory accesses. So our big insight with this was actually the idea that Wasm gave us this really nice target that was easy to instrument and easy to deploy across all of our platforms. And so looking forward, we want to look at using this insight into domains other than data races. So data race is just one kind of bug you can encounter in systems. But often there are a lot of different things you do encounter when you're fuzzing applications or trying to record and replay applications. And so one thing we have been looking at recently is extending the Wasm R3 that you heard from the previous talk to support new domains and APIs, potentially Wally, so you can run Linux applications that are recordable with Wasm, and maybe even Rust, which I think would be very useful for the robotics folks. This would involve doing replay for a number of additional things over what R3 currently does, for things like sockets, signals, communication, and threading. And kind of in vein of our data race debugging, we envisioned that we'd be able to do some sort of fuzzing of these replays and leverage this combination of some sort of instrumentation diversity and platform diversity to explore the state space of replays much more than we could without, and scale it out like we did with Wasm and give us a robust, diversity-oriented record replay system. So to kind of summarize, our grand vision for Wasm is to enable debugging, profiling, recording, any of the stuff you want to do with analyzability of programs across devices, across application domains, with minimal instrumentation, which we can make up for by the scalability of Wasm across a number of targets. And so we really think this can pull applications out of very restrictive, deeply embedded ecosystems and actually make them easily debuggable and analyzable. So yeah, to conclude, I kind of hope this talk was interesting and hope that you see some potential in Wasm as a debugging target that we can embed across different domains. Thank you.
For maybe one or two questions.
Thanks. So, you have a class of bug here, that is a timing bug, basically, right? Data races. So I don't think these conclusions would necessarily extend to other things, and other types of bugs. And what you've seen is, we're varying devices and we're getting different results, right? But because there's a timing issue, what happens is you've got different processors with different relative CPU versus memory access versus I/O speeds. And when you vary those things, you trigger different types of data races, right? So to me, what might conceivably be very interesting is not necessarily like coming up with this broad collection of heterogeneous platforms to test on, but rather a single platform where you can maybe vary the speeds of the relative type of operations, maybe by inserting no-ops or something like that. And just have some dials where you dial up and dial down relative speeds to trigger these type of data races. So I don't know, do you have any thoughts about that?
Yeah. So I think that's interesting. I think the main thing with regards to this is I'm not sure if you have seen our talk on performance analysis using Wasm. But one thing that we see is that different heterogeneous targets are actually incredibly hard to model. So essentially, I think what you're proposing is that we find a way to insert timing delays that could provide a profile that would be similar to that of running on different platforms, if I'm understanding correctly. But it's actually incredibly hard often to do things like that because, so for example, if we have a microcontroller running like a RISC-V processor and a server class x86 machine, even if you run with 100% instrumentation on the x86, you're likely going to be faster than the lowest instrumentation on a RISC-V. So there might be some interleavings that you may just never see unless you were to insert like an absurd number of maybe no ops or delays. And kind of the second thing is it's good to test these on heterogeneous targets, especially if you are deploying them on heterogeneous targets, because if you're using a data-driven approach, it's always better to use your to perform any statistical or machine learning analysis based on things that you actually expect to encounter in the wild. So I think there is definitely scope to do things with just varying timing. I think it's much more involved in terms of how you can affect the interleavings using that, and it would require quite a bit of effort, I think, into either diving into the operating system or driving into the Wasm engine and forcing certain kinds of interleavings. Does that kind of make sense?
Yes and no. Like just take a given processor, right? I'm sorry. So I said yes and no. I mean, so just take a given processor, right? If you have different types of memory with that processor that's got different relative speeds to the CPU, or you modify a hard drive, right? So now you've got faster, slower I/O, and you've again modified the timing of the system. I think that will also trigger data races, right? So you really, I mean, unless you're going to model every platform with every possible combination, permutation of memory type and disk type, and this includes like future like disk types, right, that might come out and get installed, you're not gonna cover everything, right? So it might be better, if you could find a way to just even on a single platform, just examine a range, a way to play with different speeds, and then hopefully automatically test across a range of relative, performance of different sorts of components.
Yeah. Actually, that's a good point. So you could make changes to like clock frequencies and like, I don't know, caching, your memory and things like that. And that definitely does impact your execution environment. So I think that's why when we formulated like our Heisen factor, we try to be generalizable in terms of, it could be any parameter that affects your execution environment. So it could be that you're slowing down I/O or slowing down memory or cache. In particular, we looked at platform diversity because it's kind of a nice feature of Wasm to be able to run it across, and we don't have to do as much work in modeling and creating like these complex interference patterns. But it's certainly a direction where it could be taken.